Hello, I welcome you all. The problem reads locate the center of gravity of the volume. The material is homogeneous. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So here they're asking us to find the center of gravity, and they are telling us to say the material is homogeneous. The material is homogeneous, and we want to find the point where the gravity, okay, where all the weight for this particular body will be concentrated, which is the center of gravity. So let's define what homogeneous is for a material. So we are saying a material is homogeneous. A material is homogeneous when this material These material properties, these material properties are the same at all points throughout throughout the body. Okay, so a material is said to be homogeneous when the material properties are the same at all points throughout the body of that particular object, right? So, e.g., in this case, we are saying these material properties would include density, it would include Young's modulus, okay, the elastic Young's modulus. It would include the Poisson's ratio, okay. What else? Of course, we are also saying the gravitational field is uniform and so on and so forth. So the the centroid in this particular case coincides with the center of gravity, and this center of gravity, this is where uh, the weight of this particular object, this volume, is concentrated, right? So if this body had a certain value of W, the weight, we want to find that point where the whole weight itself will be concentrated, and we are calling that point as the center of gravity, right? So let's dive into the problem. When you look at this particular body, it is symmetrical about the z-axis. Of course, we do have x-axis here, and from this particular figure we know that the x bar is equal to the y bar, which is just equal to 0. Okay, it is 0. Okay, it is 0 meters, right? So the only location we want to find this time around is along the z-axis. So what we are going to do is we are going to make a section of a disk, a very small disk. Let's make a section of a disk. We can even make the topmost disk, no problem, doesn't matter, or the middle one, doesn't matter. So imagine we cut a small disk. Okay, so this is what we've cut. We've cut a small disk like so. All right, right. Okay, there we go. So that is our disk you've cut, and then it has this area here. It has this area there, right? And this disk, it has some thickness. This thickness here, this disk has this thickness. Imagine this thickness. let me show it. So imagine this disk, it has this thickness there, this thickness of along the z axis, right? This thickness is along the z axis, and this thickness is dz. Very small thickness. This is just a very small plate that we've cut, but circular, right? So the area for the area that I've shaded in blue, this area here, this area is going to be equal to, this area is going to be equal to um, this area is going to be equal to the radius pi r squared, right? But we know our r in this particular case. We know our r, we can either pick the y. We know y and the x are the same functions. So let's pick what is available right now. That's the y. So this r is equal to y, and therefore this area, we're saying area is equal to pi r squared, but we know that our r is equal to y, and therefore this area will be equal to pi y squared. Okay, and then what is our y? We have the function y squared is equal to 2z, and this area is going to be changing, right? You've seen, as we keep on moving from the top coming down, it's going to be governed by this particular function, and therefore our area will be equal to pi. We replace it by this particular function, which will be equal to pi to z, right? So if we were to write the volume of this small disk, the volume is going to be equal to dv is equal to this area times dz, right? Is that fine? And then this becomes equal to pi 2z dz. Is it okay? Great. So this is our small volume of this disk. And now what we're going to do is we're going to integrate this volume along the what? Along the z-axis. It's like we're expanding it, okay? But it's been governed by this function, y squared is equal to 2z, right? So that we find the volume, right? So that's what we're going to do. So this time around now we are going to do what is called moments of volume, right? And then we make the direction where the direction of make z bar as our as subject of the formula, right? So we have z bar. Let me also define another property before I go ahead. We also have the small centroid or axis, centroid axis for this particular disk in the z direction. This one is equal to z curled is just equal to z. Okay, so let's go ahead now. Z bar will be equal to integral of this z curled dv divided by the total volume dv, and we are integrating from we are integrating with respect to the z-axis, so this will be from 0 to 2, 0 to 2. So z bar therefore is going to be equal to integral 0 to 2. This z curled, the centroid axis for this small disk is z, and then dv we said is pi. Remember this dv, this one here, This is the one we are getting right now. Just want to remind you so that you don't forget. We are getting this dB that we already defined. This is the one we are getting, and then we'll come and plug it here, right? Plug it there like so. So this is what we are doing right now. So that is pi 2z dz, right? So divided by from 0 to 2, we do the same. That's pi 2z 2z dz. Okay. So rewriting this properly, we'll factor out the constants. We have a 2 pi there, integral from 0 to 2, 0 to 2. Okay. And then z squared dz. We do the same at the bottom. We integrate from 0 to 2, just z dz. Okay. All right. And then we continue. Then our z is going to be equal to, we integrate this now. Let's do the integration. Z therefore will be equal to, this can go, right? This can cancel out. If we did the integration, we're going to have z to the power 3, z cubed, z cubed divided by 3 over this, evaluating it from 0 to 2, and then z squared over z squared over 2. We are also evaluating it from 0 to 2. Great. And then once we've done so, then we have z there like so. We plug in all the values. We are going to have 2 to the power 3 divided by 3. Of course, the other part gives us 0, divided by 2 to the power 2 divided by 2, right? All right. So what does this give us? It gives us, this gives us 8 divided by 3 and 4 divided by 2. So 2 by 4, 2 by 4. We cancel, we cancel, we cancel. Then z bar is therefore going to be equal to 16 divided by 12. And then simplifying this further, we are going to have 4 divided by 3. And therefore, z bar is equal to 4 over 3 meters. Okay. Right. So this is the final solution. This is the point along the z-axis where the center of gravity lies. Mind you, we've already found the other values. We said x bar is equal to 0 meters, and so is y bar. Okay, great. Right, so I hope the video was helpful. If it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.